Hello guys, welcome back to a new video on mass transfer theories. I hope you have subscribed to the channel Chemical Engineer. So in this video we are going to discuss about various mass transfer theories. So basically these all are the old theories that were proposed by some researchers after doing some research. So basically they are the principle for how mass transfer takes place. So let's start the video. Subscribed, and I am Sai Yadav. Okay, so what are mass transfer theories? So mass transfer theories are the conceptual models. They are generally based on the principle of phase boundary. So what is phase boundary? So in order to determine what is phase boundary, so suppose we have one drop of water. Now air is flowing from this direction. So always mass transfer takes place when this air particle, suppose this is all are the air particles, when these air particles wait a minute. So okay, so this is a drop, when this is a air particle, when this air particles comes in contact to this surface, then and only then there is a mass transfer. So that is the phase boundary, that is phase 1, and this is air is the phase 2. So the boundary between two phases is the phase boundary. Next, this all theories are the simple and old theories. So all, yes, it is of course conceptual, but they are of course effective. So general application are in mass transfer with chemical reaction. Okay, so the first theory is the film theory. So this theory was proposed by Whitman in 1923. So what he assumed as his principle for determining this theory was that the flow in the boundary is always laminar. So I hope you all know what is boundary. So I will discuss it in later part of this video, but suppose we have this liquid filled in the vessel, and here we have gases flowing from this to this. Then certain concentration, suppose the gas is, we are absorbing the gas, so suppose the concentration of gas here is Ca1 or Cai, then here the gas concentration would increase or decrease based on the boundary, or we can say based on the concentration of liquid. So that's not our dish to discuss, so let us discuss. So in this theory, film theory, mass transfer takes, it was assumed by Whitman that mass transfer takes place from solid surface to a flowing fluid. That is, we have some solid surface, from this solid surface mass transfer takes place to a fluid. So what are his assumptions? So first assumption is the mass transfer occur at steady state. So at steady state there is no effect of time on anything. So change in quantity, suppose concentration with respect to time, is assumed to be 0. Hence, so there will be no change in concentration. Now other example is diffusion. So he assumed that the mass transfer is occurring due to diffusion only through a stagnant fluid layer at a phase boundary. So here we have this wall as a stagnant phase boundary through which the mass transfer takes place of fluid from one to other end, and the concentration which is same as that of bulk fluid. So suppose we have this film. Now concentration here, suppose here we have fully a liquid and its concentration is CAB. CAB is the bulk concentration. So bulk concentration means concentration at of a fluid in a bulk, that is all everywhere. Here it is a fluid, so concentration here is bulk concentration. Now this is a film, so in this film mass transfer takes place, and after coming out the concentration of this will be same as bulk concentration, which may or may not be same as this one, CAB. So here we can say CA dash, which may be or may not be same as CAB. So this is how he described that the mass transfer is taking place through a film and in the diffusion, mostly a diffusion part. Also he expressed that the Na equal to N, that is the Fick's law we have discussed, that this term is almost negligible because diffusion is the main, which is the driving force. So Na equal to dA dCA by dZ. Suppose this is the length of this is Z. So this is how he performed the experiment and found that film is only the main part for changing the concentration from one to other, that is the mass transfer taking place. So this is the basically how I was explaining. So this is a graph of film thickness versus concentration. So as the concentration of, okay, so we have this film as discussed in this video, in this picture. So all the fluid first comes to the interface. So this is the interface. So first the fluid comes to the interface, then it passes through a stagnant film of thickness delta and again goes back to the bulk phase. So the concentration at first the fluid is CAB, as we can suppose it as CAB. After coming contact with interface, its concentration changes from CAB to CAI, and after mass transfer its concentration again changes to CAB, that is at the bulk. So this is what the film theory proposed, and always that CAI is he proposed that the film thickness is linearly varying with the thickness of the film, but in actual case it is not true, and true concentration profile is somewhat like parabola. This one, that is changing from interface concentration to the bulk concentration, is parabolic in nature. So this is all the derivation. So from this figure we have here flux going as Na at Z, and the flux coming out will be Na Z plus delta Z. Suppose for this small element Na Z plus delta Z will be coming out from this small element, and at steady state rate of accumulation will be 0. So from mass transfer or from general mass balance equation or flux balance equation, we have Na at inlet minus Na at the flux at outlet equal to 0. So applying limits we get this equation, and in place of Na we keep diffusivity term, that is dAB dCA by dZ, and in integration of, and after simplification we get del square Ca by del Z square. Applying boundary condition in the equation of Ca equal to this one, so from this we get integration this equation, we get Ca equal to what we can say Z. So A into Z plus B. So this is what we get after integrating this equation. So after integration we get this term, and applying boundary condition, that is Ca equal to Ci when z equal to 0, so we get B equal to Ci, this is this term, and at z equal to delta we get Ca equal to Cab, so we get Ci minus Cab into z by delta term. So this is how we get the concentration profile from this equation with in terms of z or delta. Okay, so from this theory the major learning will be that Na equal to minus dAb dCa by dz, and dAb dCa by dz from this equation can be calculated as Ci minus Cab divided by delta. So in order to test dAb by delta with the mass transfer coefficient, so here we have liquid phase, so we use Kl. So Kl is the mass transfer coefficient, so this will be equal to dAb by delta. So we can say that for film theory, mass transfer coefficient is directly proportional to diffusivity. Okay, so this is what the major learning from this film theory is. Moreover, if the film is not laminar, if we can consider it as turbulent, then film theory says that the Kl, that is the mass transfer coefficient, is directly proportional to d raised to n. Okay, so what is n? So n is nothing but a constant, n equal to 1 for laminar and n equal to 0.8 for turbulent cases. So this is what we must remember, that from film theory we get film mass transfer coefficient is directly proportional to diffusivity if laminar case is considered, and raised to diffusivity raised to 0.8 if turbulent case is considered. Now from next theory is the penetration theory given by Higby in 1935. So the film theory came in 1923, then later 1935, that is almost 14 years after, we get the penetration theory. So diffusivity is not the main concern in this theory, and Higby proposed that diffusivity is not important actually for mass transfer. So he considered the sample of rising bubble. So suppose a gas bubble is rising up and liquid is falling down, so we have absorption, counter current absorption. So this liquid elements flow through this surface of the bubble, wet it, and then at the bottom goes down. So this is what his principle is. So here is the schematic. So liquid element comes from top, slides to the surface of bubble, and then goes down after getting a complete mass transfer. So from this theory the assumptions are unsteady state mass transfer. So here we will have the term dCa by dt. Yes, so here in this equation we have dCa by dt term. So unsteady state mass transfer occurs to a liquid element as long as it is in contact. So it is important to remember that all the mass transfer takes place until the liquid element is in the contact of the bubble. So equilibrium exists as the gas liquid interface. So yes, so this liquid flowing down will be in equilibrium at all over the surface of the bubble. Then each of liquid stays in contact with for the same period of time. So suppose this bubble, so this liquid element slides down in suppose 10 seconds. So next liquid element will also take 10 seconds to slide down and do its mass transfer. And here we have contact time relation. So contact time relation is bubble diameter divided by the rising velocity. So generally we have velocity equal to distance traveled divided by time taken. So nothing, just rearranging contact time will becomes diameter of bubble, because that is what the distance a liquid travel is divided by the rising velocity of the bubble. And this equation is the what we have derived in the same way for this penetration theory. So but here in this case we have dNA by dz is not equal to 0, but it's equal to dCA by dt. So by this we get this equation. And in penetration theory we get the main that is, after integration we get that liquid phase mass transfer coefficient is directly proportional to root of diffusivity. So in this penetration theory the main learning is that this mass transfer coefficient is directly proportional to diffusivity and is inversely proportional to the contact time, root of the contact time. This is Tc. So if in exam we are asked to find what is mass transfer coefficient according to penetration theory, and DAB is given, T can be found out by this equation, so we can find out what is instantaneous and what is average mass transfer coefficient. Okay, so this is all about penetration theory. Next is the surface renewal theory. So penetration theory failed because it considered that the contact time is same for all the cases, but in actual condition it is not same. So in penetration theory this assumption was changed by Danckwerts by giving the surface renewal theory. So I hope you know who is Danckwerts. If you know, so you can let me know, or else let me tell you. So Danckwerts was a great scientist. He gave many theories on catalysis. So yes, so he gave the surface renewal theory. So and this theory is applicable to turbulent flow conditions also, because in this theory we have laminar case. So if turbulent case is considered, then the time for contact may not be same, hence this theory failed, and Danckwerts gave a surface renewal theory in 1951. So we assume that unsteady state mass transfer is taking place at interface, then probability of getting suppose liquid elements are going here, here. So he assumed that the fresh liquid element may come at the place of this element at any time. So it will have equal probability of getting replaced as this element at this place or any other place all over the surface. Hence all the elements can be replaced, having the equal probability of getting replaced at any time by the fresh element. So the major learning of this theory was KL equal to, it was similar to the penetration theory, but here he has considered that it is directly proportional to D into S, where S is the fraction of surface area renewed in unit time, that is meter square per second, area replaced per unit time. So this is what surface renewal theory has gave us to know. So this is the summary. So for film theory it is applicable to only steady state. KL is directly proportional to diffusivity, or KL is given as D by delta, and model parameter. Okay, so he considered that the thickness, film thickness, play an important role in mass transfer. Next is the penetration theory, which considered an unsteady state mass transfer, and these two are the equation of mass transfer coefficient, and it proposed that mass transfer coefficient is directly proportional to the root of diffusivity, and here the main parameter to control the mass transfer is contact time. Then came the surface renewal theory It is also applicable for unsteady state, but here he has considered that this S is the element surface area renewed in unit time as the main to determine the main parameter to determine mass transfer, that is the surface fraction of surface area per unit time. Next we will discuss about boundary layer theory later on. Okay, so this is the boundary layer theory. So in boundary layer theory, what was proposed is the boundary layer is something that boundary layer is something at which the velocity of the fluid particles is equal to 0.99 of the free stream velocity. I hope you know free stream velocity. It is given as u infinite. So the velocity of a fluid particle equal to almost same as the free stream velocity. So free stream velocity is the velocity at which we have the minimum forces acting on it. Suppose so here we have on, suppose this is a flat plate. Now in flat plate the fluid particles at almost in contact with the plate has the velocity of 0. Why? Because of the no slip condition. Okay, so here the velocity will be 0, and as we go away from the boundary the velocity increases and it reaches to the free stream velocity, that is the velocity at minimum forces on it. So at position when u equal to free stream velocity, the thickness or the thickness that is what achieved to determine the free stream velocity is known as boundary layer thickness. And also we have velocity equal to 0 at this point, and concentration of a component at this surface is supposed as CAI, and as and when the particle goes up in the boundary layer, its concentration changes according to this equation, that is Ca equal to Ci minus 0.99 of Ci minus Cab, where Ci minus Cab is what we will be discussing in the course known as transport phenomena. So in transport phenomena we will discuss how this equation we can derive. So as of now, remember that always the concentration at any point from interface is always less than what it is at interface. So at concentration, suppose at interface is 100 units kilomole per meter cube, or we can say 100. So at bulk it will be suppose 0. Let us assume it will be 0. So at bulk if we consider, so Ci minus 0.99 of Ci, so always the concentration from the edge will keep on reducing as we go on boundary layer. So from this equation, that is the Sherwood number I will be discussing in the next video. What are different mass transfer or dimensionless number in mass transfer. So Sherwood number is a relation between the diffusivity and mass transfer. Let me see. Yes, Sherwood number is developed for diffusivity change to determine the diffusivity. So Sherwood number shows the relation between the diffusivity and mass transfer coefficient, and is given as 0.332 into r raised to 0.5 into Schmidt number raised to 0.33. So no need to remember this, but the main aim to remember from this slide is we have two Sherwood numbers, Sherwood number average, Sherwood number instantaneous. So both have different equation. Here we will consider length of the plate. Here we will consider x distance, that is at instant. Okay, so this is what the learning. So from this we can determine the mass transfer coefficient. So from this, if we take it here, and after rearranging we get that KL is directly proportional to diffusivity raised to 0.66. So this is what boundary layer theory states. Okay, so these all are basically the mass transfer theories. So if you ask why to learn all these theories, so basically it is important to learn all this theory from the catalysis point of view, because all this theory plays an important role while we are experimenting with the catalysts. So mass transfer always follow any of these theory, and most recent one are beaten or some other theories, but for our course we need to remember these four theories, that is the surface renewal, boundary layer, then we have studied film theory, surface renewal, film theory, penetration theory, and boundary layer theory. So these four theory are important for our case, and from all this theory, if suppose asked what are we getting as a final result from these theories, so your answer should be that we are going to get relation of mass transfer coefficient with diffusivity from all these theories, and we will come to know that different parameters that play an important role while mass transfer. So we have discussed that boundary layer film thickness, contact time, and surface area per unit time plays an important role for determining or uh, getting the mass transfer. Okay, so we are done with the mass transfer theories. So I hope you will like, share and subscribe to the channel. Okay, so thank you for watching the video. I hope you will subscribe it. Alright, thank you.